Okay, Anjali.
Okay, I'll start. Good morning, sir. Good morning, friends. Today, Tanita and I will present about a wearable device to monitor back movements using inductive textile sensor. Next. Um, okay. A short introduction. So, this device is developed to monitor back movements such as forward bending, lateral bending, and twisting, and provide feedbacks. These feedbacks are aimed to encourage user to change their posture while they go on throughout their daily life and to reduce postural stress that can cause a disease called low back pain, which is very common in healthcare workers. So the inductive textile sensor is made up of conductive materials arranged in a loop of various shapes sewed on a fabric. Then the results are transferred wirelessly and can be accessed through a smartphone application on the user's phone. Next. Now for the fabrication method, the sensor is made up of a conductive material, in this case a single copper wire with diameter 0.14 millimeter that was sewed on an elastic fabric in a zigzag pattern that forms an inverted T shape. Like here in the picture, we can see the inverted T shape. The purpose of the inverted T shape is so that the horizontal part is placed on top of the lumbar region of the back, which undergoes different strains based on the type of movement. For example, if the movement is forward bending, there is less strain on the lumbar region. If the movement is twisting or lateral bending, there is a different strain on the lumbar region. And the vertical part, which is the T, which is this one, what do you call it? That one. It aligns with the spine, and the circuitry leads up to the circuit box at the very top of the vertical part, so that it does not disturb the user. Next. And then the elastic fabric is affixed on the back of the leotard, like the picture here, so that the leotard can be worn by the user. It is chosen because it is tight and comfortable and can be worn throughout a user's daily life. For example, underneath a underneath a uniform or other typical garments that someone wears throughout their day. And the wireless circuitry that processes the feedback consists of a high resolution inductance to digital converter board that collects the value from the sensor, which is the conductive copper wire in the inverted T shape, and it is then transferred to the microprocessor via I2C protocol. The microprocessor then transmits the data to the user's cell phone using Bluetooth, and then the data can be opened and stored on the user's phone using a smartphone application. Next.
So to test the device made by the researchers, so they did simulation and also application on a person. So first, before the application on a person, they did the simulation. So the simulation was done using ANSYS 17.2 electromagnetic suite to estimate the inductance produced after bending forward. Yeah, so they found the value, the estimation of how much inductance that will be produced. The stretching percentages used were 104% horizontally and 132% vertically. These were also tested before by asking a person to wear the garment, and then they were asked to bend forward, and then the stretch percentage were measured, and then the values were then used for the simulation. So this is the result for unstretched condition, and this is the result for the maximum stretch condition. So they have an 8.8% increase, and yeah, it is feasible to be used as a sensor for the forward bending movement. And then they also test whether the zigzag motif will affect the inductance. They then test the simulation without the zigzag motif, and this is the result in the unstretched condition, and it is way smaller than the one with the zigzag motif. Yeah, so it really affects the inductance produced. And then magnetic field was also tested, and this is the magnetic field produced in the horizontal part of the inverted T in the lumbar section of the back. This is the lumbar section, and then it could be seen that the green area here has a higher magnetic field compared to its surroundings. It means that the sensor is more sensitive in monitoring forward bending of the trunk. Yeah, so it could be used to monitor the forward bending since it has good sensitivity. As we have known, the magnetic field is the one that causes the changes in inductance, so that's why a good magnetic field is needed for the sensor. And then after the simulation, they test the prototype. And before the test, inductance value was measured on unworn leotard using tweezer, and the value is 4.5 micro. And then the value obtained is 2.2 has a 2.2 difference with the converter board. So the purpose of this test is to know if whether the converter board could produce a reliable result or not. And then for the test itself, a person is asked to do this kind of movements. Bending forward, this is lateral bending, and this is the trunk rotating. And this is the result produced. Aside from measuring the inductance, inertia measurement unit was also used to determine roll angle. So we know how much they bend forward, what angle is produced when they bend laterally or rotate their trunk. As we can see from the result, the roll angle here corresponds to the inductance signal. But as we can see here, as for the right and left lateral bending and also for the rotation, the inductance produced is a little, and it couldn't be well discriminated. So the sensor is not suitable to measure lateral and rotation movements. And then this is the result. I made the table here to conclude the results. And then the signals produced are stable at around this value during maximum forward bending and at this value while standing straight, as we can see from the graph earlier here. So yeah, it produced a stable result. And there is a 4.4% and 2.64% difference of inductance between simulation and experiment in the condition of pre-stretching and forward bending respectively. This is the table that shows the result. And it shows that the simulation and the experiment match because they only have a slight difference. And aside from the test done before, there was also an interference test because magnetic fields are prone to change, thus causing inductance change. As what I've said earlier, the inductance depend on the magnetic field. And then the tests were done using copper spool, metallic element, magnet, cell phone, and human hand to the unworn prototype. As we can see here, this is the test for the copper spool, metallic element, a magnet, cell phone, and this one is the human hand. And the maximum inductance changes were 0.01%. Yeah, this value here respectively. As we can see here, the cell phone has the highest interference for the result of the sensor, and I think this is because of the electromagnetic radio waves produced by the cell phone, because the cell phone, the Wi-Fi of the cell phone was on. That's what the researchers said. And then another interference test was also done, but at this time the prototype was worn by a person. And the test was done only using cell phone because cell phone produced the most inductance change interference. But when after seeing the result of the from the graph here, there were no changes done. There was no significant changes in inductance when putting the cell phone in the back pocket. After they this one after they put and then they do the forward bending. The person do the forward bending. Yeah, there is no difference. No significant difference. And stable signals were produced. So for the conclusion from this paper, the wearable device could aid people with low back pain by monitoring back movements, but only the forward bend, not the lateral and the rotating trunk. And then copper wire was used and sewn in zigzag pattern, which could increase sensitivity. And then stable signals were also produced, and it means that it could be feasible for real life applications. That's all from us.
Okay, thank you, Anjali and Tanita. Maybe group one, Andy and Ezra, would like to ask question.
Can the inductive sensor be changed to the capacitive sensor or resistive sensor in this application?
Okay. Group two, what is your answer?
Yes, maybe, but I think
If resistive sensor,
yeah.
yeah. Previously, there is also a resistive sensor that has been used to monitor back movements, but for capacitive, I don't think that is. But so resistive is possible, but I don't know about capacitive. Maybe it is possible, but it's gonna be tricky because there has if capacitive there have to be two electrodes like that. So I don't know how it's gonna be applied.
And also for the inductive, as what Badini has mentioned on the previous lecture, it is good in measuring movements. And yeah, lateral the bending is related to movement. So I think the inductive sensor is better than the capacitive.
Okay. Andy, any questions?
Is it possible to use this device like for when we do sports?
Yeah.
Yeah, I think it's possible because the aim of this device is because it's comfortable. It can be worn throughout the day whenever the user does his activity. So if it includes sport, then it can also be worn, I'm sure.
Yeah, but I think it will be less effective because di kalau sport itu kan kayak spontan, but for this test is only for, I mean for this device it's only for people doing work which is not as spontan as the sport. Jadi yeah, it would be better if it was used for the working only, not for sport. But yeah, it could also be used for sport.
Okay. I have questions. So what is the original paper here? Where is it? The source, you don't put it here. The original
yeah.
reference.
Oh ya, sorry. Lupa ya, Anjeli.
Sorry, sorry.
Ini nggak bisa di
Mungkin
escape.
bisa kita lihat. 1 minute, sorry.
Wait. Tunggu sebentar. Yeah, I don't know what happened, but error. But I'll just show the paper. Wait a minute.
Yeah,
It's in the report, right? You put
Oh yeah,
files.
but yeah, it's our mistake. We
in the
forgot
report.
on the presentation. This one.
Okay, what year is it? 2019.
2020.
2020.
Yeah.
Okay. Okay, can you go back to your presentation again?
Okay.
Are there no? Can you show me the zigzag pattern?
Sorry, sir.
Can you show me the zigzag pattern of the sewn copper wire?
Error. Wait a minute. It couldn't go to the previous slide.
Can you repeat again then from the
Okay.
beginning?
Yeah. Wait. This one.
Yeah. So here the zigzag pattern basically is only in the vertical part. Yeah.
No, it's if you zoom in, it's zigzag all over. Gimana ya? For both it is zigzag. If you zoom in, kayaknya.
The zigzag
Coba the next slide.
Wait. Ini not to.
Nggak jelas sih.
This one.
So yeah, the tiny one. So it's like this. Even the horizontal part also zigzag, sir, but it's in a rectangular loop, so it doesn't look that.
Yeah. Where is it? Because the horizontal one, like just straight, right? Straight and then rectangular.
Oh, the zigzag one mentioned by Angela is not this one, but can I go back to the paper? I think there will be a better picture at the paper.
Yes. Make it clear.
Okay. Yang ini kan, wait. This one. Ya kan Angeli? Angeli? Yes, sir, this one. The spike here.
So how did I get to the idea of making it a zigzag?
It's to increase the, I think, I don't know. It's to increase the sensitivity because the inductance is influenced by the length of the copper wire, right? So if it's in zigzag, so overall it will be longer.
And it will produce a bigger magnetic field when compared to the straight line. So
yeah,
they try to use the zigzag.
Okay. Okay. So second question is so then here the more sensitive part of the sensor is the vertical part of the sensor rather than the horizontal part.
Horizontal, sir. Where's the picture?
Because when you bend forward or backward, actually it is the vertical part that is bent more, right, compared to the horizontal one.
But I think it's also apa yang lumbar part because when we bend and then the stretch itu kayak rada ada juga di bagian bawahnya gitu.
Okay, so but yeah, maybe the two are stretched, but which one is actually plays more role to increase the sensitivity?
The
vertical part or the horizontal part? The vertical part is because it is the one that actually attached to the lumbar, right? To the backbone, to the spine, right?
The spine.
So intuitively thinking, intuitively should have been more sensitive compared to the horizontal part, because when you bend, it is that vertical part that is stretched more. What do you say?
I think it's still more on the
Please wait a
bit
minute.
lower.
Which one is more sensitive?
Actually, if according to this study, the ones that's more sensitive is on the horizontal part, because they based it on a previous study that it is the lumbar region that can differentiate between movements, because kayak kalau forward bending there is more stress on the lumbar, there is less strain on the lumbar region, and if it's lateral bending, it's different kind of strain like that.
And they are also asked to bend without bending the knees, like I think it's more kerasa di lower one.
Yeah, but the lower part is, you mentioned just now in the presentation that when the person rotates or bending horizontally like this, it is not that sensitive, right?
Because the lateral bending ya, sir.
Yes.
Because if it's lateral bending, ini kan kayak a movement. I think the sensor is sensitive only for the movement if it's like this, because this is the back part. But if it's lateral bending, it's like this.
Yeah, I understand that part, but then why is it not sensitive in the lateral bending? Because if the more sensitive part is the horizontal part, then it should pick more than think, compared to if it were the vertical part. So when like this, when you bend, for example, laterally, then this will bend something like this. The horizontal part will also bend, right? If you bend like this. If you bend forward, the one bending is actually only on this part, forward bending is only this part, the vertical part, right? This part, there is a bending there, but I'm not sure. The magnetic field may maybe.
I think it's because it's placed on the back gitu. Jadi in my opinion, if it's lateral bending, it should be placed like at the side part, because it moves like that. And I think it produce a lesser inductance because it is put on the back part, and so there's only like a small stretch made.
Yeah.
That's my opinion.
So when it bends forward, so from this part doesn't change much.
I think it contributes also, but not as much as this one, as the lower, as the one here.
Okay. Yeah. Another question. Can you go back to the what do you call it? The presentation file, please? Yes. The interference. Yeah. Is there any interference from the motion from other motion of the wearer, besides, of course, from the smartphone?
I think sebentar, maksud sir tuh kayak ada interference lain selain
Yes.
dari
From the motion, from other motions beside. Yeah, I don't know, from when walking, as Andy mentioned, when the person is doing sport, from walking, from running, from sitting, etc.
Nah, that kind of interference was not tested in the in the research in the experiment. So yeah, there's no data about that. They only measured when the person is standing straight and then she or he bend forward, and then if there's a smartphone or if there's another material. Yeah, so they don't test when the person is running.
Okay. Then finally, what is the sensitivity or resolution of the sensor? The sensitivity and resolution of the sensor, and maybe accuracy, if you can mention all these parameters, so that we can compare it with other, like Ezra asked, with resistive sensor or capacitive sensor.
Wait. Since I think they only measured the forward band, the maximum, and this is the average. I think it's
Can you enlarge it in the slideshow so that I can read the table?
Oh, okay.
Better. Yeah. Okay. Can you please explain what is ND? What is ND there? ND.
Wait. ND. Ya ampun, aku kira Andy. Manggil Andy. Andy is no data.
Yeah, not Andy.
sorry.
No.
It's no data. No data. No data is was given.
Not mine.
Yeah, so they only record this one. They only told this data.
Do they have any calibration data that shows the relationship between the angle and the inductance change? So not, for example, now you put only the data like when it is straight and then when it is maximum forward bending, but are there any calibration data where it relates, whether it is linear or non-linear?
They only show this graph here.
And they do not do any calibration, for example, that relates the angle of the bending with the inductance change.
No. Yeah, they only show this graph here.
So you cannot say anything about its sensitivity resolution, can you?
No, because they only measure like at a certain point, like when it's maximum and straight. So there's no kayak nggak ada di setiap forward bending itu, kayak di setiap step-step dia forward bending itu nggak dikasih tahu.
Okay. So it is not that good sensor then, so far, because it just measures the on and off then, straight and maximum bending, but in between you cannot know the angle. What is your impression of this sensor?
I think if it they should test more parameters, like that one, the how the roll angle and the what is it called, inductance is related to one another, instead of just showing this graph here.
Okay, thank you, group 2. Let's move.
Thank you, sir.
On forward, to group 1. Group 1. open, so you may start your presentation.
Okay, thank you, Pak Dedi. Good morning, Pak Dedi. Good morning, friends. So today, me and Ezra will give a presentation about textile-based inductive soft strain sensors that is a wearable device measuring the multi-axial hip joint angles. We use this paper made by Tavasolian et al. So for the introduction, wearable electronics can provide data of pressure, biosignals, and biochemical markers and strain. Actually, we can use the OMC system, optoelectric motion capture system, but instead in this journal we use the flexible fiber base. It is due to the spatial limitation of OMC system reduces the ability to use these systems to track everyday activities where they could be highly useful for sports like running. And there are three types of flexible fiber based. There are resistive, capacitive, and inductive. And in this paper, we use the inductive. It has one of the advantage is like they do not require specialized materials or a synthesis. They can just produce it with conductive wire or thread. For the experiment, the stretchable conductive copper coiled elastic thread, or we can call it CCET, was fabricated using a spur machine made by themselves. So the fabrication machine, it is consisted of 4 rotary actuators. 3 of them is used to pulling the stretchable wire through a guided path, and another one um, another one rotary actuators used to spar the copper wire around the elastic thread. As you can see a picture here, this is the illustration of how they make the CCET. They use the copper wire to wrap around the elastic thread, and this is the product of it. So the CCET, it form rectangular loops, as you can see picture D. It has 8 times 2 area. The sensor were attached to stretchy sports shorts using a zigzag C-wing stitch to create a patch. As you can see, picture A, B, C. Why they uh, put the sensors right there? It is due to when you do motion, like motion, those 4 parts, they do uh, something different than before. They do motion. And why they were just 4 sensors? Because the LDC1614 chip can only um, simultaneously measure the four sensors. And picture number A, it is optical markers. As you can see, this components where it put at the end and at the start. It is um, for for um, to determine the sensing range.
So now we move on to the properties of the sensor. They create the sensors. The first one is they are easily to produce because the smart inductive sensor like this is only require a spare machine to coil a copper wire around the elastic thread. And this sensor consists only 3 perimeter loops, which is lower than the other sensors in different literatures that are usually have like 20 perimeter loops like that. And by using these fewer loops, the sensor become highly sensitive towards the electromagnetic fields in the surrounding environments. And when it is tested, the sensor was sensitive to devices that are less than 5 centimeter nearby. But in the application, the noise is not really disturb the result. And then the third one is that it is not showing any hysteresis when it is lower than 30% of strain or below 4 hertz. This is because if it's higher than 4 hertz, then there will be causing the mechanical lag of the CCET sensor component. And the error for this test of hysteresis is just 1.43%. And then the fourth properties is that when it is used, the sensor is used for long period of time, there will be a drift of baseline signals. And when it is tested, it is found that the sensor was stable over a period of 2.7 hours within 0.48% with a minimal noise equal to 0.05 change of under static conditions. The 0.48% strain is because of the external factors such as computers, antennas, and other ferromagnetic objects that will disturb the electromagnetic fields of the sensor. And then the fifth one is the sensor can track strain accurately, and it just have an error of 2.43%. And then the sixth one is that when the sensor want to be tested to know that it can track the fast movement, the author tests it from 0.1 hertz to 20 hertz, and the sensor can track up to 20 hertz, where the fastest human motion is just 10 hertz. So it means that the sensor can track the fast movement of human. And above the 20 hertz, the sensor will show a small inconsistent peak. And the next one is that the error was found that it is less than 1.63 degree. So what I mean by that is that the authors test this sensor to 12 participants. They have to run for 10 minutes in the treadmill at a speed of 2 meter per second, and that they are put the raw signals to the algorithm machine learning, and then the machine learning will separate the signals to different categories, different angles. The first one is sagittal planes. This second one is frontal, and the third one is transversal. And it is shown that the error for these 3 planes is 0.63, 0.08, and 0.15 degree respectively. However, when it is tested to bigger motions, when it is tested to smaller motion, it can be seen that the transfer planes is smaller than have smaller error. But when it is tested to bigger motion, it is found that the sagittal planes has the lowest error. And then the last one is that this sensor is sensitive, but it needs to be combined to be embedded to the textile that is elastic and resilience, because if it's not flexible enough, it will directly affect the performance of the sensor. And if it's not resilient enough, it will affect the accuracy of the sensor. So next, these are the signal produced of the sensor. So as I mentioned before, the sagittal, the error is not that much, but when it is in transversal planes, the predictions and the motion, we can see the different color of in this graph. This is when they are all running. And then, yeah, next. So the conclusion of this paper is that the first one is the smart inductive sensors is proven to have ability to track a multi-axial tide movement during running with the error less than 1.63 degree. And the sensor shows a little drift if they are used in such a long period of time. And the third one is that the sensors have the ability to capture motions at high frequency and with a strain range of more than 450% per second. And it also shows not shows any significant hysteresis up to the frequency of 4 Hertz and the strain rate of 186% per second. So that's all from us. Thank you.
Okay, any questions from group 2? Angeli and Tanita.
Why elasticity and resilience affect the sensor?
That is because the sensor is really is embedded to the textile, and therefore we really need the textile that is stretchy, and when the participant move, it will affect the geometry of the sensor that is placed in a different part of this, and yeah, that will affect the electromagnetic fields to one another sensor, and that will affect the sensitivity also.
Okay, thank you.
Angeli?
Can this sensor be used only during running or any other sports that involve thigh movement, or just generally throughout the day? Maksudnya kayak bisa dipakai continual gitu nggak, atau kayak harus pas berapa itu?
I think they intended to use this sensor more on sports, but I think they can use it on daily life, our daily activities, but I'm not sure what's the advantage of measuring it at daily basis.
Yeah, as what Andy said, it is correct. It can be used. I think, yeah, we think it can be used in daily life, of course. But the purpose of this making this is to track if for injury or for tracking, like tracking pants. So we know the movement, the muscle movement and something like that. And but in this paper, they said that it's still not be tested to like long term, because they need to test it if it can be washed, or if it can be yeah, like to if it can be washed, or if it can be used for really long term, like that. So we still don't know if it's if it is able to be used in long term.
Okay, thank you.
Okay, Ezra. So what is that, Ezra, and what is that optical markers do? What are they for?
They exist for the sensing range. They use OMC system 2, the optoelectromagnetic. Yeah. So that they can um, um, so that they can prove that this device works.
I don't get it yet. So
So they usually so as I said before at the introduction, they actually they can use or usually use, or perhaps they uh, before, so they actually they've done this before, but I think in a different way. I think they use the OMC, and I think that works. So that they use that OMC to determine whether this device could actually works, since this flexible fiber based is advantageous on having easier to be fabricate, and for and for I think for uh athletes purposes too.
Ya, so ini maksudnya OMC kan, sir, opto electric motion maksudnya, sir?
no, there's look at the fiber A. There is optical marker there. What does it?
Oh,
Why is it there? What is it for? Because I thought it were inductive sensor, but why are there optical markers there?
so they said that if the inductive sensor is not um, really working, there are alternative way to be used, like capacitive or resistive, like that. And so they said that they prepared the alternative way too.
Yeah, in this way, what is that way? That alternative way?
So that optical marker is used, I think it's used to like detecting the kinematic human motion too, and um, yeah, it helps the to like, yeah, it helps to read the kinematic human motion, sir.
Using what? How do they read it from the optical markers?
Andy, can you explain it?
Using algorithm. There was
Because the optical markers does not give any electrical output, right? Yeah, this thing.
If I'm not mistaken, they
Okay, let's move on.
Sandy?
let's move on. Yeah, otherwise we're just stuck there. So yeah, please pay attention to the details. Yeah, what kind of measurement why they need to do this, because the idea is about inductive-based sensor, but why do they still put optical markers there? What for? Yeah, it cannot be there for nothing, right?
Yes, it is an alternative way, sir, as I mentioned
Yeah,
before.
alternative way, but I want to detail why they put there. How do they measure it? That's because it does not send any electrical signal, right? So how do they do the measurement using the optical markers to, as you mentioned, kinematics? I know, I understand the kinematics because I teach biomechanics also, but what I mean is how do they capture that kinematics? How do they know the kinematics from the optical marker? What kind of systems do they use? Okay, so can you please explain? So the coil here, the electromagnetic field is actually is being produced by the coil in the surrounding the elastic thread, right? So
Yes.
what is the material of the thread here? What is the elastic thread material?
Elastic thread.
Yeah, is it cotton? Is it nylon? Is it silk? Is it what, polyester? Is it what?
Is it? It is a coil.
The coil is the shape, yeah, the shape of the winding,
Coil.
the winding of the copper wire form a coil around surrounding the elastic thread. The thread material itself, what is it?
Actually, when I read this paper, they did not tell us what is the specific elastic track that they use. They just said that the elastic thread that have the diameters of 850 mu a micrometer.
850
So
micrometer. Okay.
yeah. So yeah, they just mentioned that, but they didn't say what kind of elastic thread that they use.
Yeah, they
Okay.
just said elastic thread.
No, nothing, no information.
No, sir.
Okay. Next, why do they need to make it coil? Why, if they make just the pattern there, the rectangular pattern, it will be enough, right, to make it as a inductive sensor, right?
I'm sorry, sir. Can you repeat the question?
Why did they need to make the coil pattern? Because if it were just the inductance, then this rectangle would be enough. This rectangular shape will be enough to make it inductive already. But what is the role of the coiling or the winding using the spur machine to make a copper coiled elastic thread?
I think it improves the accuracy of the um, the result.
How does it improve accuracy? So here they wound it first. Then after that, this copper coiled elastic thread were made into this rectangular. But if it were just like, for example, just the pattern like from the group 2's presentation, just copper directly, yeah, copper directly, you could also make it like this, and then it becomes already an inductive sensor. Or just plain sewing like this, it can be also inductive sensor. But why what is the advantage of that? They make it first roll like this and then put it into that rectangular sewing pattern.
As Andy mentioned before, it like make the signals become more accurate, and because they use like bending, and they detect the muscle movement like that. So they
accurate or precise or sensitive, which one? It's different, right? Accuracy,
yes.
precision, sensitivity is different. Which one of this?
Sir, the sensitivity, I mean, sir, because
And how come? How come they increase the sensitivity if you mention sensitivity?
because when they move, it will stretch, and it will affect the electromagnetic what is it called, electromagnetic fields, and it will make the wire become stretched. So I think the copper wire there is used to capture uh, the rotary movement of this of uh, the electrical, like electromagnetic field like that, so they can capture the bending and also the rotary part, I think.
There is no rotary part there. It is just part of stretching, the same as the group 2 actually. Yeah. So no rotation motion in the hip in that sense, yeah, because it is just put in some particular part of the hip. Okay, I will just conclude it here. So please, group, any of you, if you read in the details. Yeah, read the details. Do not just the overall structure, but you have to be able to understand the details, to read between the lines. Yeah, so you understand why you have to ask questions. You have to be critical when you read papers. You cannot. So the meaning of this assignment is not for you just to copy paste the figures and maybe some important information there in the slide and then present. But I would like you. This is including all groups, yeah, not only group 1, but also the details of the presentation. Why do they need to use that? Why do they have to do copper coiling? Why not just directly sewing? Why are there need to be 4 places there? What are the advantage? What is the accuracy? What is the calibration curve? Do they do calibration? How do they calibrate? So when you read papers, your mind, your brain has to be moving. Yeah? It's not. I'm not teaching you to copy paste here. I'm teaching you how you can critically assess and evaluate other people's work, so that then you can be critical to yourself as well when you later work your own project or your assignment. There you make your own sensor, then you know what aspects that you need to pay attention to. So this is the main point of this presentation. Not, of course, the to introduce you to the how the sensors are playing their role in the real world. In this, of course, in the research, what are being researched there, but also for you yourself to be critical on assessing their work, and not only uh, presenting their work, but you have to be critical. What are still missing there? Yeah, including group 1 also. Yeah, group 2. What are still missing there? What you think can still be improved from their work. So if you are to repeat this experiment, what can be improved? That's what I want. Yeah, not just plain explanation, not just plain presentation. Yeah, do I make myself clear to all of you?
Yes, sir.
Yes, sir.
So please prepare better next time. Don't just the surface of the paper, but really go deep into the paper. If possible, maybe go read also the references. Okay, I